Hi everyone, we are going to be going over another example of a reaction that proceeds via a full octet resonance structure. So our context is we're taking an alkene and we're reacting with HCl. Notice how there's a chlorine already bonded to the alkene. When we react our alkene with this hydrogen halide, HCl, we will electrophilically add a proton and form a carbocation intermediate. So again, our decision is, well, what's more stable, the carbocation on the left carbon of the double bond or the right carbon once we've reacted and added the proton? If we added the proton here, the positive forms at the adjacent position. If we add the proton to this carbon, the positive forms here. And let's classify the carbocations. This one is technically tertiary alkyl, and this other one here is technically going to be secondary benzylic. So the fact that it's secondary benzylic inherently means that it's more stable than the tertiary alkyl, if you refer back to our notes about carbocation stability, the ranking. But there's also another reason why this would be more stable. The chlorine atom is directly bonded, and therefore it can resonate its lone pair. When it delocalizes the lone pair, it will form a double bond to the carbon, and the chlorine is now positively formal charged, but the structure is now a full octet resonance contributor. Remember, carbocations are incomplete octet structures. And the combination of the benzylic character, remember phenyl means benzene ring, there's actually resonance stabilization around the benzene ring of the positive charge and this full octet resonance. And both of those effects are enabling this carbocation to be lower energy, more stable than this carbocation. Okay? And again, here the positive is not directly bonded to the chlorine. The chlorine is one removed. So if anything, this chlorine is functioning as an electron withdrawing atom. There is an electron withdrawal, and remember that destabilizes a carbocation. Electron withdrawal will destabilize and raise the energy of a carbocation. However, in this case, the chlorine was electron donating because it could sp2 hybridize and delocalize one of its lone pairs, which would exist in a p-orbital, to form a pi bond to the carbon and give us this full octet resonance structure. Okay? So in the second step of the reaction, you would have the chloride ion primarily attack this carbocation because this forms to a much greater extent than the less stable tertiary alkyl alternative. And we could show the chlorine attacking at that carbocation to give us our product, which we could draw. Or alternatively, you could show it attacking this contributor. It's just if you do that, we have to show it attacking the pi bond and then breaking that carbon-chlorine pi bond. Either way, we're going to get to the same product, where now you have two chlorines at that position, and you have this as your final product, ignoring stereochemical outcome. Okay? So again, these two examples we've given in the last couple of videos are meant to illustrate how you need to think about carbocation stability, and that is you need to be meticulous. You need to say, how is the carbocation stabilized? Yes, it's important to say how substituted it is, but you're also looking for other electronic influences that could potentially either add stability or introduce instability if you had, say, withdrawing groups. Both of those are very relevant considerations. Don't fall into the trap of thinking tertiary is always more stable than secondary, right? What are these? Are they tertiary alkyl and secondary alkyl? If so, tertiary alkyl is more stable. But if that was a secondary benzylic, that would be more stable than the tertiary alkyl. Or if you had a secondary that had the full octet resonance contributor, well, that would ultimately be more stable than a tertiary alkyl.